All right, today we are diving deep into a world you interact with literally every day, but might never actually see. We're talking about the surprisingly complex and honestly brilliant engineering behind the humble gear tooth. So, let me ask you this. What could a giant wind turbine and a tiny little wristwatch possibly have in common? I mean, one is harnessing massive amounts of power from the wind, the other is just meticulously keeping time. The answer isn't just that they both have gears, it's a little deeper than that. The real secret, the thing that connects them, is the actual shape of their gear teeth. It's this hidden world of applied geometry, where every single curve is painstakingly designed to pass power along smoothly, efficiently, and without failing. To really get our heads around this, we have to start with the main character of our story, the one fundamental shape that pretty much makes our modern world go round. It's called the involute profile. Now that sounds technical, I know, but think of it as the all-purpose champion of the gear universe. The shape itself is actually super elegant. It's the path traced by a point on a string as you unwind it from a cylinder. And that specific curve is mathematically perfect for making sure that as one gear turns another, the speed stays absolutely constant. So why is it the king? Well, first, it gives you that perfectly constant velocity. It's also relatively easy to manufacture with incredible precision. And the way the teeth make contact, it's just fantastic for smooth, efficient power. And this isn't just a hunch. Research from Zhang and others in 2023 points out that this precision is exactly what minimizes tiny errors and stress on the gears, which makes them super reliable. But, while the involute profile is the go-to workhorse, engineers are always pushing things. And for some really specific jobs, they need something totally different. After all, one shape can't possibly solve every problem. Sometimes you don't even want a constant speed. Or maybe you need to operate with way less stress in a super tiny device. For jobs like those, you need a different tool in the toolbox. And this is where we see some really cool alternatives. You've got cycloidal gears, which you'll often find in things like clocks. As Zavyalov's research suggests, they're great for continuous meshing with potentially less stress. And then you have elliptical gears, which are just fascinating. According to work by Liu, these are designed on purpose to create variable speeds. They're perfect for certain machines that need that kind of irregular motion. But even our hero, the standard involute gear, isn't always perfect right out of the box. Engineers are in a constant state of tinkering and refining that shape to squeeze every last drop of performance and life out of it. And sometimes, just a tiny, tiny change to the tooth's shape makes a world of difference. See, at really high speeds, the sharp tip of a standard tooth can kind of crash into the base of the next one. It causes stress, wear and tear. It's not good. The solution? Something called tip relief. As Pedrero noted in 2023, by just subtly rounding the tip, think of it like sanding the corner of a puzzle piece so it fits perfectly, engineers get a much smoother contact that can dramatically extend the gear's life. And the modifications get even more clever. I mean, what if a machine only ever turns one way, like a winch or a power generator? You don't really need the tooth to be equally strong in both directions, right? This is where asymmetric teeth come in, and it's a brilliant idea. Engineers can actually design the drive side of the tooth, the one doing all the hard work, to be thicker and stronger, while the coast side, the one just along for the ride, can be shaped differently. This kind of custom design massively boosts the gear's strength and wear resistance, right where it counts. And hey, this isn't just some theory. Research from Allwinter-Schett and Gonsalves back in 2021 really confirms it, saying that modifying the geometry for that preferred direction can significantly augment its load-bearing capacity. It's a real game changer. Okay, so we've got all of these amazing designs, these tiny micro-modifications, but how do engineers actually test them? How do they know they'll hold up under immense pressure and incredible speeds? It's a really good question, isn't it? You can't just build a billion-dollar turbine, cross your fingers, and hope the gear profile you chose was the right one. You have to know for sure. Well, the answer is powerful simulation. Before a single piece of metal is ever cut, engineers use these advanced computer models to see exactly how the teeth are going to interact. They can simulate all the stress, the friction, the heat, all at a microscopic level. They have a whole digital toolkit for this with things called finite element analysis and loaded tooth contact analysis. Basically, these super powerful tools let them predict all the complex ways a tooth might bend or deflect, and they help them understand how the load gets shared from one tooth to the next. It's absolutely critical, especially for developing gears with new, advanced materials. This is modern engineering at its absolute finest. So we've looked at the standard profile, all the specialized shapes, the incredible science behind designing them. What's the big takeaway here? The crucial point is this. The gear is not some simple cog. It's a masterpiece of engineering. It's a piece of applied geometry that has been, and is still being, constantly refined and reinvented to make our entire modern world possible. And that just leaves us with a final question to chew on. As our technology demands more power from ever smaller spaces, think electric cars, next generation aircraft, what new, unseen gear shapes are being designed right now that are going to drive our future? Thanks for watching.